Hello, everyone, and welcome to Office Hours with the Meter Environment team. Today's session will focus on soil water potential measurements in both the field and lab. And we're shooting for about 30 minutes of Q&A with our experts, Leo Rivera and Chris Chambers, whom I will introduce in just a moment. But before we start, one housekeeping item. If you're watching this video and you think of a question you'd like to ask our science experts, we encourage you to submit your questions on our website at metergroup.com. And then someone from our science and support team will get back to you with an answer via email. All right, with that out of the way, let's get started. Today, our panelists are application specialists Leo Rivera and Chris Chambers. Leo is a research scientist and director of science outreach at Meter Group. He earned his bachelor's and master's degrees in soil science at Texas A&M University. And there he helped develop an infiltration system for measuring hydraulic conductivity used by the NRCS in Texas. Leo is the force behind application development in Meter's hydrology instrumentation, including the Saturo, HyProp, and WP4C. He also works in R&D to explore new instrumentation for field measurements of water content, water potential, and hydraulic properties of soil. Chris Chambers operates as the Environment Support Manager and the Soil Moisture Sensor Product Manager here at Meter Group. He specializes in ecology and plant physiology and has over 12 years of experience helping researchers measure the soil-plant atmosphere continuum. Thanks for joining us, guys.
Happy to be here.
Yeah, thanks.
We haven't done this in a while. Good to
It's
see
been
you.
a little while. Agreed.
All right, let's get started.
Okay. First question. Can you elaborate more on how to translate a soil moisture release curve to unsaturated hydraulic conductivity in the lab? And this is a question after a webinar that we didn't get to, right?
It sounds like it is. It's an interesting way to go, a route to go. You can't just take a soil moisture release curve and go to unsaturated hydraulic conductivity. You have to take other measurements. And so that's in the HyProp when we're making our soil moisture release curve measurements, we're also making the measurements necessary to calculate unsaturated hydraulic conductivity through Darcy's law and based on the tensiometers at two different heights and
that's right.
That change.
So if you could do this in the field as well if you've got a soil water retention curve or soil moisture release curve and water content at 2 points.
Yeah, water content and water potential at two different points. You would need both because you need to know that change in water potential at the two different points along with the change in water over that time period. And we've actually experimented with this a little bit and presented on this in a webinar a while back and are continuing to do more work in this area as well.
Right. But if you're in the lab and doing the work, especially if you're interested in saturated hydraulic conductivity, pop it on a KSAT and get it. Unsaturated, that's why we got the HyProp, right?
Yep, exactly. Yeah, so you have to use the right tools to get the measurements. There are ways to estimate these parameters through models, but those are purely estimates. They're not hard measurements. So.
Right.
All right, next question. What is your opinion on comparing water release curves generated in the field by the sensors with curves generated in the lab with pressure plates in core samples?
Oof. Okay, that's a tricky question.
It's kind of a two-parter though, right?
Yeah, it is a two-parter.
Because field measurements and lab measurements complement each other.
For sure.
So leaving the pressure plate out of it, which has some baggage, let's talk about field measurements, like when you'd want to generate a field soil moisture release curve. And you can do that if you have matrix potential sensors and water content sensors co-located. And you actually get really helpful information from that. So the field is telling you what's happening. It gives you that spot, that point in time, in space, and it's going to be messier than lab data.
Yeah.
Right?
Yeah. No, the field, it is, you would definitely have to know how to clean up the field data to really get a good retention curve, especially when you're looking at wetting versus drying curves.
Right.
I typically recommend looking at the drying curve from field data because you're not dealing with response time as much there. It's a more consistent response. Whereas wetting data can be a little messy when you're trying to do retention curves. But I do absolutely think, like you said, Chambers, that they complement each other.
That's right.
Yeah.
And the reach in your field data is going to be greater than just the small soil sample, right?
Yeah.
The other things happening in your field environment are going to affect it.
Yeah. And we've done some work actually comparing field versus lab measurements, and you can actually get really complementary data that actually compares quite well. Or is also the times where you get data that doesn't compare well. And that oftentimes has to do with some of it has to do with spatial variability, depending on where you take your samples versus where your measurements are made. And also it has to do with how you prepare your sample. For especially when you're looking at repacked versus intact soil samples. But also, I mean, just to touch on the last part of this measurement, some of it also depends on the methods that you use.
Exactly.
I mean, methods like pressure plates have their limitations, especially when you're trying to push into the drier range with contact issues and equilibrium issues. And so you have to be careful with that. And yeah.
What's about the range minus 500 kPa? You really can't go much drier than that in pressure plates.
Yeah. So oftentimes people try to push them down to that 1.5 bar, that 15 bar point. And we constantly see equilibrium issues. Really, once you start getting past about 1 bar is where you start to see equilibrium and contact issues.
Because the equilibrium, the sample has to equilibrate throughout the entire sample.
Yeah, yeah, and sometimes, especially some samples, you get separation from the plate that causes issues, and yeah, there's just a lot of things that can go wrong there. So yeah, you just have to be careful when comparing those methods.
But the lab, to get back to the lab just briefly, and there's a ton of data on pressure plates historically. And bigger databases on the high prop. But when you bring these samples into the lab, what you get as opposed to just doing it in the field is this intrinsic soil property.
Yep.
And not all of these other field variables that could be confounding your interpretation.
Yeah, exactly.
Okay. Next question here. Is soil moisture affected by soil salinity? And if so, how can we measure the actual soil moisture and avoid the soil salinity effect?
This is more of a technology question or issue than anything else. I mean,
that's right.
Soil moisture intrinsically itself is not affected by salinity. It doesn't change because of salinity.
You're going to have the same volume
of
water based on the salts in the soil.
Yeah. So I don't know, Chambers, you deal with this more
the
than
technology,
anybody else.
But that's right. The technology, soil sensing, because we're measuring the electrical properties of the soil for most soil moisture sensors, then the electrical conductivity is one of those electrical properties. And it can change how you're sensing, let's just say dielectric, since that's what most sensors use, or capacitance. It's going to affect both. But many sensors are robust to a certain level. Our capacitance technology is solid up to about 8 to 10 decisiemens per meter of saturation extract EC.
Yeah.
So below that, you can effectively ignore the effects of salinity on your water content measurement. Once you start getting up around 8 decisiemens per meter of saturation extract, then you're going to have to pay attention to the EC and possibly do a calibration.
Yeah. Yep. Now, beyond the actually measurements of soil moisture, I still think it's super important to understand that salinity because it can impact how available that water is for plants and stress that you can see in plants due to the salt. And so
particularly in estuarine or managed agricultural systems.
And then a follow-up along those same lines, are there any experiments that check the soil salinity effect on soil water potential?
Soil water potential is a different story.
Yeah.
You absolutely, if you break out the water potential equation for soils, then your osmotic potential is a component in that, and that's very much affected by the salinity.
Yeah, absolutely. The great thing is if you know the salinity, it's actually pretty easy to calculate the osmotic potential.
That's right.
So there's a pretty simple relationship that you can use to make that measurement or to make that estimate of osmotic potential from the salinity measurement. So that's really neat to be able to actually do that. And especially important when you're making measurements in the lab with two tools, one like the high prop versus WP4C, where the high prop measures matrix potential and the WP4C measures both matric and
Total,
osmotic potential. And so it's important to understand that and how you actually make those measurements and how to correct for those things.
And depending on your measurement technology, matric potential can often be independent from EC.
Yeah.
So you might not get that measurement interference. Like in a tensiometer,
Yep.
the solutes pass in and out of the ceramic.
Yep.
So you really don't get that effect on your measurement.
Yeah.
All right. This next question we get quite often, I guess, in our webinars and other places. Is there a difference between placing the Teros 21 sensor horizontally versus vertically in measuring water potential?
I'm a horizontal fan. No, vertical fan.
Yeah.
Yeah, that's right.
Yeah.
But really, it's just about how water moves through the soil.
Exactly. Yeah. Yeah. I mean, the measurement of the sensor itself doesn't change how depending on the orientation, but what does happen is how the water moves through the soil is definitely impacted, and it can create a gradient from the top side of the sensor versus the bottom side of the sensor that can cause issues with the measurement. And so, yeah, I'm along with Chambers. I'm a proponent of the vertical installation. It just helps mitigate those issues and creates the least resistance to the flow of water through soil.
And the main, we say that after putting out videos of installing it horizontally. The main thing to bear in mind is you don't want it to be flat, where water can actually pool on the surface of the sensor.
Yeah.
What is the utility of saturated hydraulic conductivity for crop irrigation management?
Yeah.
This is kind of a tricky one to answer, but really relevant to irrigation management.
Yeah.
A lot of people think you put water on the soil and you're immediately going to see it in your sensor.
Yeah.
It's immediately going to be available to the plants. And it takes time.
Yeah.
And it can take a differing amount of time depending on the antecedent soil moisture conditions.
Yeah.
So hydraulic conductivity is very important for how water gets to plants, but I don't think it's very, very well considered in irrigation management at this stage.
No, I would agree with your thoughts on that. And I don't know how well, I personally don't think it's super well considered in irrigation management, but I do think it's an important piece, not only in understanding how it's getting down to the plants, but also at what rate you can actually apply irrigation. Because depending on your soil type, that can change. And especially when you think about a lot of people moving to drip irrigation and things like that, not only is saturated hydraulic conductivity important, but I also would argue that unsaturated hydraulic conductivity is extremely important because that impacts how the water actually moves away from the drip lines and how it can get to the roots.
And it has a different path that it has to take with less water available.
Yeah. So in coarser textured soils, you could see a lot more vertical movement of that water coming in from drip irrigation. Whereas in finer textured soils, it's going to pull out more laterally and get actually pulled probably more into the root zone. So you need to understand that when it comes to irrigation timing and the rate that you actually apply.
That's right. And we actually see this in practice in sensors all the time where there's a substantial delay from water being applied to it reaching the sensors. And if the sensor's deep enough, you might not see it at all.
Yeah.
Because so many things are happening over a foot of soil. How quickly the water can move through, which varies, as we've mentioned, but also your evapotranspiration and uptake by plants. So it's a very important variable for irrigation management. It's just tricky to get the right number and interpret.
Yep.
So this next question is a fun one. How does boiling retardation occur in a Teros 31 sensor to extend its measuring range? Is this achieved by adding solutes to water, or is it due to specific properties and design features of the sensor itself?
Yeah, it's a great question.
Yeah, this is all about the air, right?
Exactly. Yeah. It's all about removing as much dissolved air out of the water that's going into the tensiometers as possible. But it also is a part of the design features of the Teros 31 itself. The engineers that worked on this worked really hard to limit the nucleation points in the internals of the Teros 31, because that's one of those things that causes that air bubble to form, is that there needs to be a nucleation point for that. So that means we have really clean inner shaft of the clean and smooth inner shaft of the Teros 31, and where the pressure transducer sits, all of that cavity is designed to limit its ability to cause a nucleation point. And then it just comes down to degassing the water as good as possible.
Exactly. And if you can see bubbles, then you need to stop and re-degas your shafts and your pressure transducer wells. I can't remember who explained it to me like this. It might have been Wolfgang. But how, if you imagine trying to lift up a weight with a steel chain, it can be a lot easier. But then if you have a flexible rubber band or something that you're trying to lift a weight with, each one of those air bubbles is going to expand and contract more depending on how much tension you're putting on your water column. So it weakens your water column and you will not be able to transfer as much force.
Yeah. So it's a pretty neat thing that we've been able to do without adding anything to the water. It's actually just about removing the air and allows those sensors to achieve, in some cases, well beyond 250 kilopascals of measurement range.
I think you need to be a bit of an artist to do that. I'm not that meticulous enough. If I get mine down to minus 120, I'm happy.
Yeah. I think with what we've done with the systems for degassing, it really makes it a lot easier to do this versus some of the traditional ways that we used to have to do this. So, but it's all about the tools.
Now, tell me, let's take that a step further, because at Teros 32, you cannot do that.
Correct.
Because it's going to get air entry at about minus 85.
Yep.
Right?
Yep. So there's two issues. One with the bigger tensiometers, why you can't do that. Those cavities are actually too large to do that. And so that's the beauty of the small inner shaft on the Teros 31 is it's just more feasible to actually do that. The Teros 32 cavities are too large. The ceramic also has a different air entry point. So there's things that limit that ability. But yeah, with the micro or small tensiometers like the Teros 31, it's a lot more possible to do this.
Okay, this next individual is asking, for the Teros 21 and 22 sensors, what is the measurement range that gives better precision? Do they require calibration or not?
Yeah.
So they are calibrated.
They are calibrated. Yep.
And this really just depends on the physics of the ceramic water retention curve. Right?
Yeah. And I mean, obviously the range. So our primary calibration is from -5 to -80 kilopascal. So in that range, the sensor obviously is going to measure the best because that's our primary calibration range. We do some stuff beyond that to help kind of characterize the sensors. But once you get beyond that, then there are other factors at play that can impact, like temperature and some of those things that can impact the accuracy a little bit. But it's also really hard to characterize beyond that range.
And it's because we have that inflection point in the retention curve of the ceramic where, when things are pretty wet, it's really forgiving if you get a small change in water content.
Yeah.
The calculations to matrix potential are pretty small.
Yep.
But then, a little bit of electrical noise at, say, minus 15 bar, and you get a small change in water content, that turns into a large change in matrix potential.
Yeah, exactly. And so that's where the dry range is much trickier to deal with and make good measurements. I mean, I think we do as good as possible right now in that range, and hope to find ways to make better measurements in that range. But it's tricky for sure. In the wet range, these sensors do the best. But the great thing is that they can measure beyond the wet range, and then when things come back into the wet range, you don't have to refill them. You don't have to do anything. Exactly. They're just ready to go.
It's a great tool depending on the questions you're asking.
Yep, exactly.
All right, next one. Do you have experiences measuring water potential in soilless media? What are the challenges? What is the best? Tensiometers, Teros 21, Teros 22, etc.
I found the Teros 21 and 22 to not be great in soilless media. It's mostly the contact, right?
Well, there's two things at play. It's mostly the contact, but also most of the water held in most soilless medias is really, less than minus 30 kPa or more than higher than minus 30 kPa. So you're and oftentimes it's in the 0 to minus 10 kPa range. Right. Once you get beyond that, then you start to see a lot less water. Yeah, there's not that much water left. And so it's really because of the way the water is retained in the media that most of it's in that very wet range. And tools like the tensiometers are just much better, one, at getting good contact.
I've seen them work pretty well in soilless media.
Yeah. I mean, we've done countless number of measurements on soilless media with the high prop, and that uses tensiometers, and it does a great job of making measurements in that media. But that's also what's shown us that the bulk of the water is held in the very wet range.
Right.
So tensiometers just have the precision to make measurements in soilless media, and they're just a better tool for that.
A little easier to shape into the media as well to get good contact.
Yeah, exactly. Yeah, and the nice thing is that most of these, because they stay in the wet range, cavitation is less of an issue, unless you screw up and let it get too dry.
In which case you're going to have other problems.
Yeah, exactly. I don't know. I'm a big proponent of tensiometers for soilless media. I think they're the best tool available for that.
All right. Here's a fun one. Can you talk about conditions where you might see positive pressures in conditions less than saturated?
That's
a puzzler.
Yeah. Well, I can think of a few scenarios, and I don't think these are super common, but if you do have a wetting front moving through and there's trapped air in the soil, that wetting front can induce pressure in that soil. But again, this is going to be pretty fast, and
you have to be really near to saturation too.
You would, yeah, and so I think these are pretty rare conditions, but it's not. And even in saturated field conditions, there's always a chance that there's still some trapped air in the soil.
Yeah, and you think structure might play a role in this as well?
Sure.
Where you've got a mix of like macropores and then some micropores to really mess with it.
Yeah, for sure. I think that's where that will definitely play a role. But outside of that, I can't think of. I'm sure there are conditions that we're missing, like with difference between some confined aquifers and unconfined aquifers, but. We're getting pretty complex stuff right there.
It should be fairly rare and dissipate pretty quickly, though.
Yeah. Yep.
This one is asking, how does organic matter content affect water potential? Is this something that could be calibrated to an existing water release curve?
I mean, you want to do the water release curve with your organic matter in there, right?
Exactly. Because you need to characterize the impact that it has. It does impact it.
Yep.
Because we know that increasing organic matter in soil increases its water holding capacity. Therefore, it's going to impact the water potential and the soil moisture release curve. But I'm sure there's ways to model it with pedotransfer functions, but it's really, if you can measure it to understand what that impact is.
It's going to be highly variable depending on the organic matter too. If you have fine roots that are breaking down, it's going to change over time. If you've got coarse material that's more resistant to decomposition, then it really, you just want to take the sample, do your measurements with the organic matter content, and be aware if you're getting large changes in that content.
Yeah.
All right, here's another one. Hydrocarbons, do they have an effect on sensors? And do your sensors operate sufficiently in contaminated soils?
It's kind of tricky.
Yeah. I mean, I think it depends. This is getting beyond my area.
It depends how much,
hydrocarbons.
for sure.
Can they contaminate sensors? I mean, if you're getting a large amount of hydrocarbons coming into,
I think it depends a lot on what it is. A lot of them are hydrophobic, in which case, if you're gonna change the properties of the soil or coat the sensor. I think for capacitive sensors, they should be pretty neutral for the measurement itself.
Yeah.
Since that's emitting an electromagnetic field into the soil, they're definitely going to have an effect on the electrical properties, though.
Yeah.
So it really depends on how much and what the nature of them are. It's a bit broad to just address hydrocarbons in general.
Yeah, well, that's an interesting point. That I didn't think about the fact that they can be hydrophobic. I mean, beyond the impact on sensors, it impacts how water is retained in soil because that wetting angle changes, and it's going to have a pretty big impact on how water is retained and moves through soil.
It's definitely going to, that's right. You're going to have different soil properties for sure.
Yeah.
How about this one? Can sensor accuracy be affected in any way by the type of field crop?
I think your interpretation of the sensor information is going to be more affected than the sensor accuracy.
Yeah.
It's kind of fun to go down this rabbit hole. Like, what are the factors that affect sensor accuracy? Wait, what type of sensors are we talking about right now? Soil moisture or like water content or what matrix potential?
I think we could talk about both.
Let's talk about both.
I mean, I can't think of many situations where the sensor itself is affected unless you have a huge root ball that is maybe forming because of it.
The sensor is going to detect the water in plants, just like it affects the water in soils.
Yeah.
Right. So basically you've got water carrying organic matter in the soil.
Yeah.
But your water content, unless you have like really high biomass in the soil, really high root mass right there, the only thing you'd really have to worry about for accuracy is your calibration.
Yeah.
Right. So you could conceivably have to do a custom calibration.
Yeah. Which I think is still rare because you think about the dielectric properties of most organic material is not that different than soil itself.
Yeah, right.
It's pretty close.
That's right.
And so I can't think of many situations where you would you would have to have a pretty significant increase in organic matter to need to do a custom calibration. To me, though, I think it's not really what it does to the sensor, but it's about where you need to measure. To me, I think you think about the different field crops. What I'm concerned about is what is your rooting depth, and where are the critical measurement zones that you need to be measuring.
Right, placing your sensor appropriately to answer the questions you're asking.
Yeah,
and then interpreting your soil moisture data, like at what level is the plant happy?
Yeah,
Where are your set points? Where are your critical, the zones you want to avoid for sure. So it should affect your interpretation more than it affects the accuracy of the sensor itself.
Yeah, agreed.
Talking about calibration. So what happens if a sensor is calibrated wrong? For instance, the sensor gets changed from one soil to another. Also, who calibrates the sensor? Is it meter group? Or can the end user change the calibration based on needing to move the sensor? And is it necessary to calibrate every time before use?
That's a fully loaded question right there.
Yeah, it is. And really relevant because calibration is one of the big things that can affect your accuracy, which can affect your interpretation.
Yeah. And I think we need to break it down into two different aspects of calibration. There's the calibration of the sensors themselves to make them measure consistently among different sensors.
And that's the responsibility of your manufacturer.
Yep. And so that's where we spend a lot of time trying to improve those processes to have as consistent sensors as possible.
And make it testable with a verification clip you can use in the field so that you know whether or not your sensor is properly calibrated by the factory.
Yeah. And then the other aspect of that, of course, is the soil-specific calibration.
And that's converting the electrical properties of your soil to a water content.
Yeah, exactly. And I mean, of course, that can have an impact on the measurement.
And those can be bad calibrations too.
For sure. And we've seen users do really bad calibrations.
Yep.
And so it's definitely something you want to be careful. At Meter Group, we have two soil-specific calibrations. We have our field, like our mineral soil calibration, and we have a soilless media calibration.
And in general, the mineral calibration will get you within about 0.03 meters cubed, plus or minus, in your typical mineral soil.
Yep.
And we get this question once in a while, like, what is your mineral soil? What do you mean by mineral soil? Like, when do we use that calibration?
Yeah.
And basically anything that falls in your texture classes of sand, silt, clay is going to be appropriate for that calibration.
Yeah. And we have a pretty good soil library that we use for our soil-specific calibration that fits into that general mineral calibration. But there absolutely are conditions where you may need a custom calibration.
Exactly.
Yeah.
Volcanic soils,
exactly.
like pumice, folks have wanted to use it there and absolutely needed a custom calibration.
Yep.
I've seen some really, really low density soils come across that where our standard calibration didn't make any sense. Like some soils less than 1 gram per centimeter cube in density are definitely going to need a soil-specific calibration. On the other end, it's really dense clays, maybe some heavy clays, right?
Yeah, I mean, these have to be pretty heavy clays because we do use clay as a part of our calibration, But there are some sites where you have upwards of 70, 80% clay. That's where you might need soil-specific calibration to address some of those behaviors that aren't quite captured in the typical mineral calibration.
That's right. And it's good to bear in mind that there's an immense variability of soils in our biosphere across the planet. And having one equation to capture that entire variability, it's not a valid expectation.
No,
or a reason. Let's call it
not
a reasonable expectation.
Yeah, agreed.
So occasionally you are just going to have to do a custom calibration. And you can actually generally expect to improve your accuracy if you do a custom calibration.
Yeah.
Although there's some soils that the calibration fits extremely well.
Yeah. Yeah. I mean, the one part I would stress there is if you're going to do this, follow good methods for doing this. Homogenize your soil. And we have resources out there that cover how to do this.
Our SOPs online.
Yep. Please follow those because like I said earlier, we've seen some really bad calibrations as well. And sometimes you can do yourself a disservice by doing a bad calibration and assuming that it's going to help your measurement, and it actually makes things worse.
Yep, exactly.
Getting into a lab question, what would be the performance of the high prop in measuring soil water retention curves and calculating hydraulic conductivity at the near saturation range?
Okay. Well, there's two parts of this. I mean, they're asking about one, the retention curve versus hydraulic conductivity. And there's two different aspects of that. The retention curve, phenomenal. I mean, that's obviously that's where the high prop thrives, is in measuring that near saturation down to about minus 100 kPa range of the retention curve. Hydraulic conductivity is a different
hydraulic
beast.
Conductivity blows my mind once in a while. Just imagining how the different ways that water can move through a soil based on its soil conditions. Like if you're saturated, it's pretty simple, right?
Yeah.
It's going to move one direction.
Yeah.
It's going to have a pretty consistent conductivity, and your pressure heads are going to make a big difference in the water flux. But unsaturated, that gets, like, if you're looking at an unsaturated conductivity between like minus 2 megapascals and say minus 100 megapascal, or no, let's say minus 100 kilopascals, you're going to get very different conductivities, right?
Oh yeah. Yep. Yeah. And one of the challenges with making this measurement is that, especially when it comes to measuring it with the high prop, is that we need a difference in the rate of change between the upper and lower tensiometer that is detectable. So for the retention curve, that doesn't matter, because then we're just measuring that the average major potential in the core. But to do the hydraulic conductivity measurement and to follow Darcy's law, we need a measurable rate of change difference between the upper and lower tensiometer. And for some soils near saturation, that doesn't happen for a while. Like, you don't actually see that. They just track with each other. But in finer textured soils, we actually can push that measurement further up into the range, because you start to get deviations earlier on in the measurement. And so that's where the answering this question is a little tricky, because it is dependent on soil type and how that rate of change differs. And so it can be a little more challenging for some soils to get right near saturation to get that hydraulic conductivity measurement.
Now, how well do models work for unsaturated conductivity based on like texture class? Or
they work better than saturated hydraulic conductivity.
Good to know.
Yeah, because when you start getting into the unsaturated hydraulic conductivity measurements, you do get to a point where structure is playing less of a role, and it's more so the movement in between the inner particles. And so that if you are using models that take into account bulk density, they do a much better job than they do at that than they do at measuring saturated hydraulic conductivity.
And you get like your tortuosity from your texture class, and and then your macropores really don't make a difference.
Exactly. At that point, the macropores aren't what's contributing. There's a point. I mean, there's a point, and it depends on the size of the macropores. But you can use models to estimate this, and they do. You get a better estimation from models for unsaturated hydraulic conductivity because of that than you do for saturated hydraulic conductivity.
Cool.
Yeah.
All right. What is the quickest and easiest way to install a water potential sensor in the field?
Matter transporter.
Yeah, I mean, if that was feasible.
All right. Yeah, probably wouldn't have this problem if we had that technology, would we?
No.
So this depends on the sensor selection, right?
Yep. Yeah, and then it also depends on the depths that you're wanting to measure at. In some cases, if you're trying to do deep measurements, to some extent, depending on the soil type, the 21 can be better if you have good conditions where the install tool will work, which we know there are some conditions where the install tool doesn't
21
work as
can
well.
be tricky. It can be tricky. Its form factor isn't made with ease of installation in mind.
No, but that's one of the reasons we worked on tools like the Terrace 22.
22.
Yeah, is because it really does simplify that. Now, of course, the Terrace 22 has its limitations too, but you can, especially if you're measuring within the upper meter.
Within the upper
half,
meter, drill a hole,
Yep.
push it in, drill another hole, push your next one in at a different depth, and you're ready to go.
Yeah, so that is something that's neat about the Terrace 22 is you can take a drill out there with a masonry bit on it, drill your hole. It takes probably less than a minute, and you just push the sensor into the ground.
And, there are conditions when we were at National Soil Moisture Network last year, and so where were we, Logan? And it was hit that caliche layer with a hammer drill. That still was kind of fun, but we got into there.
Yeah,
and
I mean, some soils are going to cause challenges. Rocky soils, caliche layers. I mean,
for every single device you're trying to install in soils, you're going to get challenges.
Yeah, but in many sites, especially if these are sites that are cultivated sites where you're growing, less likely you're going to run into any major issues like that, because typically those are not optimal growing sites. But you can pretty easily install those sensors. And what's really nice about those sensors is if you need to remove them at the end of the season, the Terrace 22 is something you can also remove at the end of the season.
Exactly, especially if you've got it going all the way to the surface.
Yeah.
You can just grab it and pull it out.
Yep.
This next question is asking, how does sensor equilibration time affect the temporal resolution of water potential measurements in dynamic field conditions?
Really, this is going to have the biggest impact when you install the sensor, right?
Yeah, for sure. I mean, I think when you install the sensor, and to some cases, if you have really flashy events, and some sensors might have a slight delay, like the solid matrix sensors like the Terrace 21 and 22.
But largely, it's going to be a function of your soil hydraulic conductivity, and then the ceramic hydraulic conductivity, if it's different than the soil.
Yeah, I mean, for the most part, the ceramic has fairly similar behaviors to soil
because we've composed it such that it's very similar to soil in its pore structure. The big difference is soil structure. But again, unless you have like macropores where water is just flying through it, the sensor is going to respond very similarly to the soil.
And if this is ever something you're really worried about and you have really fast, flashy events that you need to measure, sensors like the tensiometers have incredibly fast response times.
Basically seconds.
Yeah. And so if that is the thing that you're worried about, then I would use tools like the tensiometers to capture those events. But in most cases, I mean, there are some applications where I think that's important.
And if it's too dry for tensiometers, then your matrix potential sensor like the Terrace 21 or 22 is going to be perfect.
Right. And when you're in those dry conditions, your rates of change are not that fast. So those sensors are going to have no issues with that.
All right, next one. In what ways do field conditions such as freeze-thaw cycles, root growth, or microbial activity interfere with long-term water potential measurements?
I mean, this is why you take long-term water potential measurements, right? So that you can observe how these are happening and what's happening. You don't always know what is happening in there, so these can frequently appear like confounding factors. But if these are any of your research questions or things you want to control in the field, this is why you do field measurements rather than lab measurements.
Yeah.
Because you cannot capture variability from any of these things in the lab unless you've got a very elaborate, long-running experiment.
Yeah, no, because a lot of these things that we're talking about here definitely impact over time how water is retained in soil and what that water potential looks like. I think the only other thing I would add to this is there are some situations where it can impact your ability to make measurements, especially if you're using something like tensiometers, because tensiometers do not like freezing conditions.
Nope.
And so you would have to empty them during those freeze-thaw periods until it's at a safe point where you're not worried about the sensor freezing and getting damaged. But in these conditions, tools like the Terrace 21 and 22, you can leave them out. They can handle freeze-thaw cycles with no problem, and you can continue to make measurements during those periods. But outside of that, I mean, a lot of these are factors that just actually impact how water is retained in soil.
Okay, next question. How can real-time water potential data from field sensors be integrated into decision support systems for irrigation scheduling?
It'd basically be an excellent tool to do that, right?
Yeah.
Especially if you have something like Zentra Cloud,
Yep.
where your data is near real time. You can pull it in from a bunch of different sources, get alerts, and visualize the history of the data as well.
Yeah. No, I mean, I think that these sensors can play such a good role in building out these decision support tools for irrigation, because ultimately, if you have the data, you can make better decisions on when and how much you need to irrigate. And these sensors can help you with that.
Even if you don't know where to start, the sensors are going to give you an objective view of the water status.
Exactly.
And you can watch how your crops respond over time.
Yep.
See what your yields are like over time, and take a lot of the guesswork out of what's affecting your yield and fruit quality.
Yeah. I mean, if you know what the optimal ranges for water potential are for the crop that you're trying to grow, then you have the measurements and the data you need. You're like, okay, these are my bounds. I need to stay in these bounds.
Get a text message when it leaves them.
Yep. Yeah. And especially if it's, not only on the dry end, but there's bounds on the wet end too, that sometimes many crops are sensitive to being too wet, and that can impact yield as well. And these give you both sets of information.
Yep.
All right, last question here. How do field measured water potential values compare to those predicted by pedotransfer functions? And what are the implications for model reliability?
Yeah. My favorite topic.
So the functions are built on this information, right?
Exactly. Pedotransfer functions are basically a large database of data that they're pulling from to take in the properties that you put into them to estimate what either your retention curve is, what your hydraulic conductivity is. That's all it is it's just pulling in a huge data set to try and estimate based on the parameters that you input what these variables could be. And they do a decent job if you put in the right parameters. And so it's all about what you put in, but at the end of the day, it's just an estimate. It's great. It gives you an idea of what's going on. And if you can't make the measurements, you know what? At least it's helpful to understand.
Right.
But again, there are still so many things that pedotransfer functions don't take into account, or they're trying to improve those pedotransfer functions to take them into account, like organic matter, soil structure, all these things that also play a really big role that aren't as well accounted for in pedotransfer functions. And so that's why I think measurements are so critical to really actually characterize these properties.
And do some ground truthing on the models as well. As you build a model, test it against how it performs with real values from the field.
Yeah. Yep. And the more data you collect, then you can maybe build a more robust tool set of pedotransfer functions to then estimate some of these parameters from other data sets in the future. But you still need a really strong data set model or data set to build that model. And the input parameters are also very critical, because if you're going really basic and just using soil texture for your pedotransfer functions, you're going to get a pretty basic answer.
Yeah. Just like your face.
You can cut that.
You don't have to, though. You don't have to.
All right, that wraps it up for us. Thank you again for joining us today. We hope that you enjoyed this discussion, and thank you again for all the great questions. Also, if you have any questions we didn't answer, please contact us via our website at metergroup.com. Finally, subscribe to the Meter Group YouTube channel and accept notifications to see previous episodes of Office Hours and to get notified when future videos are available. Thanks again, stay safe, and have a great day.